Now that we have the tool of L'Hopital's rule at our disposal, we're just going to do a few examples using it. So we'll see what they look like and how they go. So for this first example, we ask, what's the limit as x approaches infinity of e to the x over x squared? And when we think about what's going on with each of these individually, well, e to a very large number gets very large. So we've got basically infinity on top, and on the bottom, infinity squared is basically infinity. So we do have a large number divided by a large number, so we know this is an indeterminate form. So L'Hopital's rule should be able to help us. Now these are both differentiable functions. They're both continuous on all real numbers, so we are allowed to actually take those derivatives at those points. So remember how we denote that. If we're going to use L'Hopital's rule, we should write the L apostrophe H over the equals sign just to kind of justify where this is coming from. And thinking about our side work, okay, the derivative of e to the x, well, that's the nicest derivative there is. It's just the same function out of it. So the numerator actually stays the same. And the derivative of the bottom, x squared, well, that's the power rule, right? So power comes down, decrease the power by 1, so we get 2x in the denominator. And now we evaluate this limit to see if that reveals anything. But, interestingly enough, notice, well, it's the same numerator as the beginning, so it's still going to a really big number. And the denominator is 2 times a really big number, so that's still a really big number. It's infinity divided by infinity still. This is still an indeterminate form, and it seems like L'Hopital's rule didn't necessarily help us. But the nice thing about L'Hopital's rule is you can apply it multiple times. If it's still an indeterminate form, L'Hopital's rule, it applies, we can use it, so we just do it again. So e to the x, that just stays the same. The derivative of 2 times x is just the coefficient 2. But now notice this is a new form. We still have infinity on the top, but the bottom doesn't have x. It's just a constant value of 2. This is a very large number divided by the constant value 2. Well, no matter what, that turns out to be infinity. So remember our technicalities about limits. Technically, this limit does not exist because it's not going to one specific number, but we do know that we can classify this limit in some way. As x approaches infinity, e to the x divided by x squared gets really big. It goes towards positive infinity. For this next example, now let's look at the limit as x approaches infinity of the natural log of x divided by the cube root of x. And just as we saw with the example in the last video, the numerator is still getting very large. Take the cube root of a very large number, and it's still very large. So still, same indeterminate form. We've still got natural log of x divided by cube root of x giving infinity divided by infinity. So L'Hopital's rule we shall use again. Now in this case, like we saw in the last video, the derivative of the numerator is just 1 over x. Now the bottom, remember it helps to think about root functions with their rational exponent form. So that means this is x to the 1/3 power. Oh, when we think about it that way, the power rule applies. So the exponent comes down, and we decrease the exponent by 1. 1/3 minus 1 is negative 2/3. So that's our denominator function that we get after that. So now we look at this and ask the same thing, okay, what are we looking at now? Well, as x approaches infinity, maybe it helps to rewrite these expressions with positive exponent form. So we're still going towards a very large number. I can still leave the numerator function as 1 over x. For the denominator, that's 1/3, and then that's 1 divided by x to the 2/3. Well, in this case, notice how both are getting large. I'm ignoring the 1/3 for now, but the numerator, 1 divided by a large number, that goes towards 0. And the denominator, that's still 1 divided by a very large number. That's going towards 0. So we actually have a new indeterminate form. So something to see from this example is that you're not always going to get the same indeterminate form out of it. Sometimes it changes, as we see here. Now, what can we take away from this? It seems like now we're kind of stuck with the same idea. But one thing we should always do in these L'Hopital's problems is algebraically simplify whenever we can. So in this example, 1 over x and 1/3, 1 over x to the 2/3, we can actually simplify that to one common exponent on the x expression. And after that simplification, we get this expression, 3 times 1 over x to the 1/3. The 3 came out because we were just having a fraction of a fraction with that constant, and I combined the exponents of 1 over x and 1 over x to the 2/3 to get this expression of 1 over x to the 1/3. Notice, this makes our limit a lot easier to evaluate now. This will just be, well, 3 divided by a large number. The 3 just goes to the numerator. The x gets very large because that's what our limit is looking at. So 3 divided by a very large number is a very small number. It goes towards 0. So there's always a few tricks to kind of look out for on some of these. There's changing limits that might occur in the behavior. And after we apply L'Hopital's rule, we don't always have to keep applying L'Hopital's rule over and over. After each application of L'Hopital's rule, we should try to algebraically simplify and see if that reveals more information than just the derivatives themselves, what they said. For this next example, we kind of bring a message of caution when using L'Hopital's rule. Kind of a just don't blindly use it without thinking about the circumstances that we're in. So we do a little bit of trig here, and we have the limit as x approaches pi from the left of sine of x over 1 minus cosine of x. And what I'm going to do for this example is just apply L'Hopital's right away. I'm not going to try evaluating it. We're going to assume this is an indeterminate form and see what that turns into. So let's consider what happens there. If I apply L'Hopital's rule, it's the same limit as x approaches pi from the left, and we take our trigonometric derivatives of the top and bottom. So sine of x, that becomes cosine of x. And for the denominator, 1 goes away as a constant. The derivative of negative cosine of x, well, cosine becomes negative sine, and that will cancel off with the current negative that's there, so we get sine of x. And we ask, okay, what happens as x approaches pi for both of these functions? These are two continuous functions at pi, and it really doesn't affect that we're approaching it from the left, but just to say we're coming from that direction. Cosine of x, well, that goes towards negative 1. And sine of x goes towards 0. So this should be going towards infinity, a very large number because the denominator is getting really, really small. And actually, I should be careful, that's negative infinity. So it is a signed, very large negative number. But let's actually go back to the original question here. Before we took L'Hopital's rule, let's consider what functions we're actually looking at. So sine as x approaches pi. Well, sine of x is going to go towards 0 as x approaches pi. And 1 minus cosine of x? Well, cosine of x is going to go towards negative 1. So we're going to have 1 minus negative 1, and that simplifies to 2. Notice this actually isn't an indeterminate form. If we just plugged in values into the functions as they were, we just get 0 divided by 2, which is 0. A form that we can actually figure out the value of just by looking at it. So it's not indeterminate. And notice how these give us different answers. Well, this answer of 0 is the correct one. Sine of x divided by 1 minus cosine of x does approach 0 as x approaches pi. So L'Hopital's rule actually doesn't help us for determinate forms. Functions that it does have a determinate value that we can figure out just by looking at it. So we don't want to just apply L'Hopital's rule to every limit that we see, because it might lie to us. So just to be careful on that.